Since this is an introductory course, I won't go into the details of how the convective processes and convection dynamics in the deep tropics depend on temperature and moisture. Basically, there are measures like convectively available potential temperatures, which are measures of buoyancy. So it's when you raise an air parcel from the surface into the upper atmosphere or into the free troposphere, how warm it is compared to the surrounding. So parcel temperature and the environmental temperatures can be compared to see how buoyant it is and how far it will rise before it reaches equilibrium with the environmental temperature. And obviously moisture dynamics is very important here, because if you remember, the temperature is warm at the surface, in situ temperature is warm at the surface and decreases to the troposphere. Whereas in the deep tropics, equivalent potential temperature is almost uniform because convection tends to mix it up. But when a parcel rises, the expansion and condensation of water vapor in it gives it additional heat, so it doesn't cool as fast as a dry parcel as it rises. This is what is the convection dynamics all about. So if we deal then with the equivalent potential temperature instead of in situ temperature, then some of these things become more clear in terms of the dynamics of how global warming and related moisture dynamics are going to be affecting precipitation in the mean and extreme events. Okay, so this is critical because the debate about exactly how mean precipitation response and extreme events respond still continues in terms of their ratio. For example, if you warm the atmosphere by 1 degree using our Clausius-Clapeyron, we know that the humidity will increase by 7%, but saturation humidity also increases with temperature and specific humidity also increases, so relative humidity may remain the same. It turns out that this is true for the ocean, where there is infinite supply of moisture, but on land there isn't an infinite supply of moisture, so relative humidity can decrease when there is warming. And extreme events on land are not necessarily related to local warming, because when there is heavy rain, moisture has to come from somewhere, typically from the ocean. So very few places there is a direct relation, whereas on the ocean there tends to be a more direct relation between warming and extreme rainfall events. So how the mean rainfall shifts and how the extreme rainfall change is all a bit complicated. It turns out that mean precipitation doesn't increase by 7% just because water vapor increases by 7%. In the mean global average, it tends to increase by 2 to 3%, but extreme events can in the meantime increase by 10, 20, 30%. So all these things are important, and the idea is that equivalent potential temperature captures this relation of warming and moisture dynamics better, because equivalent potential temperature includes the moist dynamics implicitly in it, explicitly in it. Okay, so let's look at some of the analysis to show how this works. So here is again surface air temperature from various reanalysis products which we have defined before. So there are some observations included in here as well, such as had crew data, and you can see that the trends are slightly or significantly different among them, so we have to be always careful of that. So surface air temperature anomalies with respect to the base period of 1980 to 2019, sorry, this is with respect to 1980 to 1999 period. The data is shown for 1980 to 2019, so fairly recent. So surface air temperatures obviously have warmed up, and all of the data and the reanalysis basically agree, even though the trends are slightly different. If you look at the surface equivalent potential temperatures from the same product, you can see that the interannual variability is more obvious here, or much higher in amplitude in the equivalent surface temperature than in situ temperature, because things like El Nino, La Nina, Indian Ocean dipole, Atlantic El Nino, Atlantic Nino, and other things that happen in the latitude band that we are looking at. So these are showing that the interannual variability is much more dramatically captured here, like the 97-98 El Nino, the 2015-16 El Nino, and some of the La Ninas, and so on. So keep that in mind as well. And the trends here are also different. So you can see that, again, they are different significantly, but in the data, the trend in surface equivalent potential temperature is 1.48 as opposed to 0.79 in situ temperature. So you can now see how the moisture dynamics accelerates the equivalent potential temperature trend. Looking at the global maps, observed surface air temperature trends from observations and the similar plot for surface equivalent potential temperature, there is some places where all the data is not available, so they are left blank, especially for this where humidity data would be needed, and so on. So you can see that there is a warming amplification in the low latitude, similar to the polar amplification that we see in surface air temperature. So here is the reanalysis surface air temperature trend, which is more complete because it's interpolated model and data, blended model and data product. So here the polar amplification is very obvious, but the impact of moisture dynamics in the low latitudes is not at all obvious. But when you look at the surface equivalent potential temperature trend, then it becomes very obvious, as well as the east-west temperature gradient, which is also very critical here, as we discussed briefly before, for things like global warming pause. Because if you remember, when this region is cold, ocean is taking up the heat, so less remains in the atmosphere, so the warming trend is slower, and this is kind of a positive feedback in the trend sense, because this increases the east-west temperature gradient, east-west pressure gradient, zonal winds, and so on as well. Okay, so the sequestration of heat into the ocean is higher when this pattern of warming happens, but you can see that that pattern is changed here as well. Okay, so looking at again things like surface air temperature and surface equivalent potential temperature with the wet bulb global temperature extremes, you can see that that relation was here. So this is the blue line is the theta E, the red and yellow lines are the surface air temperature and wet bulb global temperature extremes, and the purplish line here is the tropical land wet bulb global temperature extreme. And you can see that before about 1980, that difference was not much between the theta E and the other two measures. But when you go into the warming period since the 1980s, you can see that the surface theta E is accelerated, and that corresponds somewhat better to the global land WBGT and tropical land WBGT, as opposed to surface air temperature, which is warming, but not as much as the global theta E. Okay, and you can see the future change of the total theta E here, again comparing 2080 to 2099 to 1980 to 1999, where in addition to the polar amplification signal, you have this massive tropical amplification signal as well. Okay, so just to round that out, look at the relationship between annual mean precipitation and annual mean surface air temperature here, going from about minus 10 degrees centigrade to 40 degrees centigrade, and you can see this is for 30 south, 30 north during 1980 to 2019. Precipitation data from NOAA, and surface air temperatures and theta E from RFI reanalysis. Each point represents a bin average of data from all land grid points in the latitude belt of 30 south, 30 north. The correlation coefficient is given here, so you can see that this correlation is only 0.33, whereas this correlation is 0.98. Remarkably better capturing of the precipitation dynamics here, in addition to the extremes as well. And you can see also the extremes in wet bulb global temperature, which is very critical for health and heat waves. The surface air temperature correlation is only 0.6, whereas the extreme BGTs are correlated with theta E at 0.71, much higher here, especially if you want to think of building an early warning system. Okay, so I hope that gives you a good sense of how we still continue to learn about global warming, its impacts, and the processes that are critical to track in terms of how increased greenhouse gases to first order create warming of surface air temperature, but then it changes pretty much everything else that we have looked at, of course, as ocean warming, sea level rise, glacier melts, increased water vapor, extreme events, and so on. And here we are saying the increased water vapor and increased temperature together provide us a good measure called the equivalent potential temperature, which overall may turn out to be a better indicator of global warming in terms of its impacts on precipitation, extreme events, wet bulb temperature, health, and so on. And this will obviously translate to impacts on crops and other things as well. Okay, let's leave it there.